Welcome to Chemistry 111. This is our last full day of the semester before our final. So, quick reminder of a few things. As part of the Monday, Wednesday, Friday class, our final is held this coming Wednesday at 12:30. So, as long as you're not in quarantine or not going to be missing for some sports related activity, so you'll show up in the classroom before 12:30 for an in-person final. If you are quarantined or you cannot make it for any reason, please let me know in advance. I will send you a separate but seemingly equal online final. However, just because it's online doesn't mean it's any easier. In fact, it may be less beneficial to try to take that one. But I have to have one, as there's at least 2 people I know who are going to be missing. Now, there are still 2 more study opportunities held by SMACs and held in the basement of the library on Monday and Tuesday at 7 p.m. That is a good chance to maybe get some homework done if you do not have it done. Good chance, because remember, those points are going to help you in the long run. Those extra 50 points here from this assessment, or there are many points there from that assessment. Do not forget homework, the last little bit of officially due this Saturday. So keep in mind, I still accept things late, and grades are not due to the Monday after finals. So once finals have all been taken and that's in, I can be like, oh, hey, if you can score another 25, 50, 100 points here through your assessments, you could easily bump your grade up a letter. So I'll hopefully be able to let you know. Though having some of that stuff done in advance will make your life a little bit easier. So keep that in mind. Test 4 is also due this technically Sunday at midnight, but I have it set the actual due date for like Monday morning sometime. So even if you started it right at Sunday at midnight, you should still be able to finish it and turn it in before it like shuts off and doesn't allow you to submit it. So don't forget to do that. So what are we going to look at today? Well, what we're going to look at today is, first, we're going to look at some extra study materials that you have available for you. Then maybe, depending on how much time we have, look at some more achieve homework. Look at some review stuff. Jump around. So first thing, I'm going into the class, Google Classroom. So you have available to you essentially, let's see if I can, how easy it is to scroll down. Come on. You should have in the final material right here, final study guide. This right here is extra study material to help review for the final. What I would suggest, perhaps, is if you have caught up with all your homework, this is an excellent extra study thing. However, if you have not finished your homework, it would be much more beneficial to actually probably complete your homework, because this is not going to give you any points to do it. However, what this is ACS, which is the same company, the same business, the same organization that puts out our final. It's also made a study guide. I have a copy of it. I think our library has a copy of it, but I have photocopied it and tried to put it into relative PDFs or Word documents based on the chapters. So these various chapters cover a wide range of topics, a wide range of chapters. So they're not going to fit up perfectly, but they are a good example if you want to see how the questions get asked. These are perfectly reasonable. Jumping straight to molecular bonding. So molecular bonding is going to deal with, let's see if I can open this in a new window so we can zoom in better. But molecular bonding is going to cover our Lewis structures and our Vesper models, and it's going to cover at least 2 good chapters, if not a few more, assuming this will load. There we go. See, let's see. Let's zoom in a little bit more. So how they break this down is they will look at first some study questions where they're going to fully explain how they came to the answer, and going through a couple different topics, and then they will go into the set number of questions. And of course, I've also copied the crib. So looking at this, let's see. Yeah, we want. Let's. Okay. Okay. So. How do I scroll the dang thing over? Okay, there we go. There we go. So examples, like say NH3, which is a pyramidal geometry, reacts with BH, a planar geometry, to form the compound NH3BF3. What is the geometry around the nitrogen and boron centers of this addition compound? So the N took its lone pair and made a bond with the B, which has no lone pair. So if you to draw this, nitrogen would have 4 bonds to it, 4 electron domains. B would have 4 bonds to it. It would also have 4 electron domains. So what would be the shape? They would both be tetrahedral. I'll say that a molecule ML, can't really pick that up because it's the zoom. Okay, ML4 consists of 4 single bonds and no lone pairs. Its structure would be, so you got to look, electron domain, 4 electron domains. So it's all tetrahedral. Let's see which structure. So the shape that most describes this would be the trigonal pyramidal. Which of these guys are molecular structures are geometrically similar? So you would have to draw that out. Which of these compounds is planar? Which is linear? So these are examples of like how you go from shape to a structure. So knowing what that shape is supposed to look like, you would give a bunch of different options and you would have to go, okay, crap. So I might need to sketch out these Lewis structures. If you recognize one right off the bat, that can help you. But worst comes to worst, you have to sketch it out. Consider the given Lewis structure, BF3. Its predicted shape. So what would we look? 1, 2, 3, 4, 5 bonds, 1 lone pair. So 6 electron domains means it's octahedral. And then 1 lone pair means we remove one of it, so it's a trigonal, a square pyramid. So you'd have to review what those terms mean, what they look like. But if you have that lab, that lab that we did in the Vesper model lab is a perfect lab for reviewing this stuff, looking through the models you made. So there's a case of what is the shape of xenon F4. So you got to go draw out xenon F4. You go, okay, there's 4 bonds. Xenon should have 8 electrons, so we put another lone pair and another lone pair, so it has 6 electron domains, which means it's octahedral. And then octahedral with 2 lone pairs means it's square planar. So now let's see. This one is a perfect resonance problem of asking you to think about resonance. Carbonate. Here is described in Lewis' formulation of these structures. This means that 1, either 2 carbon and oxygen atoms are single bonds, a third is a double bond. That 3 independent forms of carbonate ions exist in equilibrium. C, that the electrons must be rapidly exchanging among the 3 forms. And D, the carbonate ion exists in only one form, and which is the average of these 3. So they are not independent. These forms are not independent. We don't get 3 of these guys. These guys are one and the same. But we are not also getting the average. We see the average, but that's because all these exist simultaneously. So what resonance actually is the electrons are moving between these structures. The electron in this lone pair is swinging like a door. Door on a hinge swings from this top right oxygen to the bottom oxygen. From the bottom oxygen to the top left oxygen, or the top left to the top right again. They are rapidly exchanging so fast that we seemingly get the average of these 3 structures. But if we were to chill this down so that it's cold enough that electrons have a more difficult time moving, you would actually see just 1 or just 2 of these structures. Because essentially, the same way as a door on a hinge. If it swings easily, but if you let the hinge rust, suddenly the door is going to be stuck in one location. It's either not going to open or it's not going to close. So the same way is if we cool this reaction, this compound down, it's going to stick in one of these situations. But just look at, so this is a perfect way just to look at some of these compounds, say, what type of questions do they ask? How do they ask them? So you get a feel of this. Obviously, memorizing these questions aren't going to help you, but knowing how they ask them will at least prepare you for what to expect. So knowing that fluorine is more electronegative than both B and P, what is the conclusion to be drawn from the fact that BF3 has no dipole, but PF3 does? So it's saying that BF bond is polar, PF bond is polar, but BF3 is nonpolar. And this has to do with BF3 is a nonpolar molecule because we have symmetry. BF3 is trigonal planar, so it's symmetric around an axis. PF3 is trigonal pyramidal, and so BF3 must be trigonal planar. that not spherically. So BF3 must be trigonal planar, might be the best option. The Tom Craze. Yeah. Because BF3 is not linear, and neither of them are really spherically symmetrical. And even so, if PF3 was symmetrical, it would not make this polar. So valence electrons. So how many valence electrons are represented in the Lewis dot structure? So just asking questions where you might have to draw this out. You might have to count the electrons. Which of these guys does, which of these molecules violates the octet rule? So xenon tetrafluoride definitely does. And NO2, I believe, does as well. And because NO2 has an odd number of electrons, and so someone has 7 bonds. All the other ones do not. Okay, so just looking at this, I'm going to move on to the next set. But which species contains both covalent and ionic bonds? You're looking at for something that has a metal combined with 2 nonmetals. So magnesium cyanide, the cyanide would have the nonmetal bond, the covalent bonds. Magnesium has covalent bonds. So you can look at these. These are up on Google Classroom in the final files. So you can go to this. Real easy thing, sigma and pi. Remember, sigma bonds are our single bonds. When we have a double bond is made up of a sigma and a pi. If I have a triple bond, it's made up of a sigma and a pi. So how many sigma do I have? 1, 2, 3, 4, 5, 6. How many pi? 1, 2. So what did I screw up? 1, 2, 3, 4, 5, 6. Oh, I think that's a triple bond. There's a triple bond there. You can't really see it because of the how fuzzy this is on my screen, but that's pi, 2 pi, 3 pi. But looking at your screen, hopefully you can zoom in. Once again, these were all photocopied by me, so it's both my fault and not my fault. I mean, I didn't tear anything out of the book, so that's kind of why it's as fuzzy as it is. But so that is an example of how they ask questions about both chapter, the Lewis structure chapter and the Vesper model chapter. We have that. We also have thermodynamics. One thing I want to point out with thermodynamics is this covers delta H, but it also covers second semester stuff, which is delta S and delta G. So not all this stuff will be directly applicable to us. So if you take a look at this, please note, there'll be some questions you cannot answer. You might be able to guess, but they are not going to be represented on this final. So don't worry too much about that. If you're like, oh, it says something about Gibbs or something about entropy, I have no clue what that is. Yeah, you shouldn't. We shouldn't know. Good. Zoom and scroll. That's a okay. Oh, dang it. So I just want to look at the practice questions. I got some practice questions to show you what you can expect for, like, say, delta H. We have a 45-gram sample of alloy, 100 degrees C is dropped into 100 grams of water at 25 degrees C. What is the final in the final temperature is 37. What is the specific heat? So this is a little tricky one, but as I said, that's about as tricky as the Q equals MCAT come. So you're given all the stuff you need to figure out the heat of the water. That heat of the water also equals the heat. The heat gained by the water is equal to the heat lost by the alloy. So looking at that, how much heat was gained by the water? It went from 25 to 37, so it's gained 12 degrees. The specific heat of the water is 4.184. And the mass of the water is 100 grams. So the heat gained by the water is 5020.8. How do I know to multiply those together? We got heat should be in joules. So we have joule, gram, Celsius. We need grams to cancel out. We need Celsius to cancel out. Now I'm going to divide by my mass of metal, 45. I'm going to divide by the temperature change of the metal, which has gone from 100 to 37, which is 63. So divide by 63, and get my heat capacity of the metal is 1.77. That's a perfectly reasonable example of this. Let's see. 68 joules of energy is energy. Okay. Volume, when a material in liquid state is vaporized and then condensed, the steps are what? So when it's vaporized, when you boil something, does this take energy or does it gain energy? Does it take energy or does it produce energy? Well, if you've ever heated something up on the stove, you should know in order to boil it, it's going to take energy. So that's endothermic. So the opposite would be when it's condensed, it would have to be exothermic. It has to release that heat back out. So calculate the delta H of the following reaction. So this is a bond enthalpy reaction. Remember, bond enthalpy is opposite of standard enthalpy. Bond enthalpy is reactants minus products. Standard enthalpy is products minus reactants. Why is that? Because it takes energy to break bonds. So I would calculate my reactants, which is 243 plus 159, which is the sum is 402. The products, which is 255 times 2, because there's 2 chlorine-fluorine bonds, it's 510. So 402 minus 510 is 108, negative 108. Negative 108. However, since there's no positive 108, all you'd have to do is one side minus the other side, and you would get the correct answer. As I made here, calculate delta. Okay, let's skip the bond energy. Bond energy. Table data. Here you go. Standard enthalpy of formation for nitrogen oxide, NO2, is the enthalpy change of which reaction? So when you form, you calculate the standard enthalpy of formation, you're looking at the change. What does it take to make 1 mole of this compound from its starting materials? So NO2 means we need 1 N and 1 O2. So 1 O2, there we go. And to get 1N, you have to have a half mole of N2. So the correct answer is B. I know that's contradictory. This is contradictory because normally we say do not use fractions as a coefficient. But in order to make 1 mole of NO2, we have to use a half mole of N2. We cannot use N because N isn't the standard form. It would not be the standard enthalpy because N is not stable. N2 is the standard elemental version. Real quick, the next one, combustion of ammonia represented by this process. What is the enthalpy of ammonia? Okay, so this is tricky. This is a tricky trap. So they give you the delta H of this reaction. So the delta H of this reaction is the difference between the products minus reactants. So 6 water and 4 NO minus 4 NH3 will give you negative 904.8. So let's figure out what we got. So NO is 90.4. If you multiply that by 4, you get 361.6. 6 water at 241.8 is for negative 1450.8. Summing those products up, the delta H of products is negative 1089. So from there, we're subtracting 4 NH3, but we don't have the amount of NH3. So we have to set that equal to the negative 904.8. So we're going to get the 4 NH3 to the other side and add the 904.8 to the other side. So we're going to say that NH3, 4 NH3 is equal to negative 184. 4 NH3 is equal to negative 184. But we have to divide that by 4 because there's 4 NH3s. So the sum, so the delta H formation of NH3 is actually negative 46. Negative 46.1. But what we did is I set up my delta H reaction, left what I didn't know out as a variable, and I had to solve knowing that we have the delta H reaction sum already calculated. Solve for the unknown. Why did I not have to include oxygen? The delta H formation of pure elements in their standard state is always 0, which is why they didn't give that to you. Let's see. Do a quick Hess's Law one. Oh, that one is actually painful Hess's Law one. I'm not gonna. Let's see. There we go. We'll do that one down right there. Gonna have to scroll over to make sure it's in frame. Scroll up. So what is the delta H of this reaction for problem number 18? So they want 3 hydrogens plus O3 goes to 3 waters. The decomposition of ozone by hydrogen. So they give us the energy of hydrogen plus water. Oxygen goes to water. And they give us the formation of ozone from oxygen. So what I would suggest we do is first calculate how many times do I have to use equation 1. I look. In equation 1, they have a hydrogen on the left. They have a water on the right. So that appears identical to the original equation, except that the coefficient is wrong. So I would have to use equation number 1 3 times. They would give us 3 hydrogens, and it would form 3 waters. Now, the equation 2, we have oxygen on the left, we have ozone on the right. Ozone needs to be on the left. So first thing I'd have to do is flip the sign to flip the equation. So it becomes negative 271. But also, there's 2 ozones being formed in this equation, and we only need 1 ozone. So if we were to half this equation, we would half the ozones and half the energy. So I'm adding negative 286 times 3 plus a negative 271 divided by 2. Because I'm using the equation 1 3 times, but I'm using equation 2 0.5 times, and I have to flip the sign. So my sum is negative 994. That's my answer. But so that's just an example of here's how they ask a Hess's law problem. Here's how they ask some delta H problems. Here's one, calculate the combustion of ethylene. So you just have product reactant. So you'd have 2 times water plus 2 times CO2 minus this guy, 1 times this guy. You do that, there's your answer. Boom. So enthalpy of reaction. So some of these, yeah, obviously we can't answer. So we can't answer what about negative entropy because we don't know what entropy is. So I'm going to go ahead and skip out of that. But what I just want to show is this is perfect examples of how these guys end up getting asked. As I said, the atomic structure, it's a little bit harder to read, but the atomic structure chapter has a look of chapter 2, the proton, neutron, electron guide. It also has a look at chapter 4, the properties of light and electron configuration and quantum. The stoichiometry would obviously be our chapter 9 and 10, I guess. Oh, yeah, let's see. But all this, as I said, is available for us. So if you've done all your homework, you got nothing else, and you want to study, and you actually want to do well, I mean, that's what you can go through. Otherwise, I'd suggest go through some of your assessments, try to finish off whatever data you've already got. Keep in mind, the hardest problems on the Achieve are way harder than anything on this final. These problems are made to be done within like 2 minutes per se. You have 70 questions. You got 120 minutes to do them. So you technically have 1.74, what that would be like 100 seconds per problem. Not all of them are going to, for God's sake, not all of them are going to take that long, but so when you get to some of the math ones, obviously, oh, geez, I gotta think about this. Oh, come on. Yeah, so some of these I didn't have good enough things to put them as a PDF, so I had to put them on Word and load them up. And so some of these are a little bit uglier than others. So bear with it. Oh God. What is this? Let's see. Can I zoom in? Where can I zoom in? Come on, where's the fuck? Shouldn't I what? Oh, I'll have to work. Okay. This will have to do for now. Okay, where's the dang scroll bar? Okay. So in a neutral atom, there are equal number of what? Protons and electrons. Which element is represented by this structure? So you got obviously I can't read this, it's so dang fuzzy right now, but you'd have the atomic number on bottom, like atomic mass on top. And so you'd look at the atomic number and go, oh, that is element blah, looking at a periodic table. God's sake. Not all of them, I guess it's just loading weird. The number of neutrons in this atom is blah. So you got chlorine 1737. The protons plus neutrons gives us the atomic mass. So 37 minus 17 would be 20. There's 20 neutrons. They're asking things like, oh, which pair of these have the same number of electrons? Which means isoelectronic. Which ion would have 26 electrons? This would also look at the atomic properties a bit. Ion is, let's see. So looking at sodium is different from sodium ion is different from the sodium atom in that the sodium ion has fewer electrons. Yeah, fewer electrons. Has a negative charge. No, yeah, no. So fewer electrons. Which term best characterizes the relationship of hydrogen and deuterium? Deuterium is an isotope. So here's a percent abundance. So element occurs and exists at 20% of this atom and 80% of that atom. The atom's mass must be nearest. So let's see. I'm assuming it's 12 and 13. So what you do, so is 13 times 0.8 and 12 times 0.2, and you would get 12.8. So the guy that is more abundance, the mass is closer to it. It's not going to be exactly 13. It's going to be somewhere between. Let's see. Just looking at these. So this is just example of there's no questions about the experiments. Valence electron state. So electron configuration. Which one of these guys is impossible? I did this one yesterday it's kind of really hard to read. But what you'd see is 1s2, 2s2, 2p6, 2d something. That one is the one that's definitely impossible because D does not appear till 3D. Even though it doesn't get used to the fourth row, 3D is the lowest D we can get. So B is definitely wrong. I'm not sure what the other ones say. They're kind of a little fuzzy, but I know that one's definitely wrong. Ground state electron configuration of a manganese atom is, so manganese, Mn, would be atom 7 on the row, on row 4. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5, whichever one that is. Species of ground state electron. So this one, you'd have to scroll over to see the correct answer. Zinc 2 plus. This guy, I say, which species has ground state electron configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. 3d10. So it's missing 4s2. When an atom loses electrons, it loses from the p first, then the s, then the d. So zinc would be 4s2, 3d10. So zinc 2 plus would just be 3d10. It's lost from the s. So I just want to show some examples of, here's how they ask us. Species is the box one. Which of these electron diagrams could represent the ground state valence electron orbital? D is the best answer. We put all the atoms, electrons in equal, and all the orbitals before we pair them up. When we pair them up, it'd be up and down, but we start them all in the same direction. Up, 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 then down, 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 or down, 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 and then up, up, up. But we don't flip them. So B is not right, even though it's closest to being right. So emission lines. Let's see. Which of the quantum orbitals can correctly describe n of 4? So this one's kind of hard. You're going to have to kind of guess this, but there's some weird rules. If n is 4, then L can range anywhere from 0 to n minus 1. So that means L could equal 0, 1, 2, or 3. So B is definitely wrong. B is definitely wrong. M sub L ranges anywhere from positive to negative L. So if L is 3, you could have negative 3, negative 2, negative 1, 0, 1, 2, 3. So that means C is wrong because you have an L of 2, M sub L of 3. So right now we're between A and D. And then, of course, the lone pair has to be, the electron has to be a charge of 1/2. So the correct answer is A. So, as I said, I didn't teach you this well enough, mainly because it's not a huge deal. It gets asked on occasion, but it's like very nitpicky for what it is. So I just wanted to, just wanted to show you those. I'm going to probably skip the stoichiometry. We're almost out of time. But so those are all available. Those are up there. And they're ready for you to look at if you so desire. In the meantime, work on your assessments. Work on your assessments. Do test 4. If you need help with your homework, send me emails. If you still need to make up some labs for whatever reason, contact me. But if you need help with the homework, I will be around. Not going anywhere. I'll be in town. I'll probably be in my office. Not always a guarantee, but I will be around. There's a study session, as I said, on Monday at 7 and Tuesday at 7. Good chance to get help on some homework. But if you need anything, just send an email. In the meantime, if not, I will see you guys on Wednesday. Good luck on all your finals. I'll hopefully see you guys next semester. And hopefully we got this worked out. So keep everyone being safe, everyone staying healthy. So thank you for your time.